Hello, everyone. Welcome back to the course on time and space complexity analysis. I am Sanket Singh, and in this lecture, we are going to continue our discussion on problem solving around calculation of worst case complexity of different algorithms. In this playlist, we have already completed that why efficiency of algorithm is important, how do you measure the algorithm with respect to hardware, and how a single CPU core system works. We already talked about rate of growth and asymptotic analysis. And even in the last lecture, I already talked about a few problems and how you can calculate the big O notation based worst case complexity for them. In this lecture also, we are going to solve around 3 4 more questions, which are going to give you better clarity that when you actually see an algorithm, how you should move forward to calculate the complexity for it. In my opinion, understanding how complexity of algorithm is calculated gets more clear when you solve more questions or you see more algorithms and try to calculate complexity for them. It's not a one time process, you need to be iterative in that, and this playlist is going to focus on that. We are going to solve a lot of questions where we will be calculating the time complexity of different algorithms. This lecture is going to be part of a bigger playlist that we are building for time and space complexity analysis to make sure that you guys get a good grip on this particular topic. So without any further delay, let's just start and let's start solving our first question. Now we have a new function in front of us, f of 7. It takes an input n. In this whole function, if you just carefully see, the only part which is dependent on what is the input is this for loop part. The outer loop goes from 1 to n minus 1, because see, from 1 it is going to less than n. So 1 to n minus 1, can I say total it is n minus 1 instructions. But now n minus 1 instruction is what? Approximately n. So we'll just take approximation that this becomes n. Then in every iteration of I, when let's say I is 1, then j goes from n to 2. If j goes from n to 2, what is the total number of iterations? Can I say n minus 2? So in every iteration of I, j do n minus 2 iterations. So I is equals to 2 also, n minus 2. I is equals to 3 also, n minus 2. Right? And so on. At last, when I becomes n minus 1, then also you'll do n minus 2 instructions. Total is what? The outer is total n minus 1 instruction. For I, in every iteration of I, you do n minus 2 instruction execution for j. This is what? N square minus n minus 2n plus 3. These are all lower degree term. So the answer is going to be order of n square. Right? That is, the growth rate of this function is as equivalent as a quadratic function. So now we have a very interesting function as a problem statement for us, right? So this is function f8, it takes an input n. This is a constant instruction, we'll avoid it. Only part of the function that is dependent on the input is this. Now just think about it. When the value of I is 1, see, I starts with 1, then you compare, then you add it to add it to the answer, and then you do some multiplication. So technically you do 3 instructions. Then in the next iteration, I becomes 2 because it gets a multiplication of 2. Then again, you will execute 3 instructions. Then I will be again multiplied by 2, and 2 into 2, I will become 4. And again, 3 instructions. Then 4 into 2, I will become 8. And again, 3 instructions. And so on. Right, and so on. So you can see, in every iteration of I, we are executing 3 instructions. So if total iterations of I is k, then we have total 3k instructions, right? Right. Okay. Now, what is the value of k? What is the value of k? Let's just think about it. In the first iteration, I is 1. In the second iteration, I is 2. In the third iteration, I is 4. In the fourth iteration, I is 8. Can I say that? So technically this is what? 2 raised to the power 0 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, so on and so forth. This is the first iteration. This is the second iteration. At last, there will be the kth iteration. At the kth iteration, I will be equal to 2 raised to the power k minus 1. See, in the first iteration, it is 1 minus 1. It is in the second iteration, it is 2 minus 1. In the third iteration, it is 3 minus 1. Fourth iteration, it is 4 minus 1. So in the kth iteration, it will be k minus 1. Can I say that? And in the kth iteration, this will be the last value. This 2 raised to the power k minus 1 will be the last value, which will be less than n, because the next iteration 2 raised to the power k will be greater than n, right? Okay, now 2 raised to the power k minus 1 is less than n. Taking log both sides, log, and we should say log base 2. We will take log base 2 on both sides. So this will become log of 2 raised to the power k minus 1 base 2 less than log n to the base 2. What is log of b a raised to the power c? Can I say it is c log of a raised to the base b? Can I say that? So this is the power c. I can say it will become k minus 1 log 2 to the base 2 less than log n, right? Which will be what? What is log of 2 to the base 2? Can I say 1? Because 2 raised per 1 is 2. So this will be k minus 1 is less than log n. K is less than log n plus 1 to the base 2, right? Can I say the maximum value of the k can never exceed log n, because k is less than log n plus 1. So can I say what will be the upper bound? What will be the tightest upper bound? We can say the tightest closest upper bound for k can be log n. And you can even see how many total instructions were there, 3k. So 3 log n will be what? Order of log n. Can I say that? And if you just carefully see, in my big O notation, I am nowhere writing base 2. See, I am not writing base 2. Why? Because there is no point of writing a base. Because log n to the base 2 can be converted to log n to the base 3 by just multiplying a constant, right? Log interconversion, log base interconversion is very easy, right? If you want to convert log n to the base 3 to log n to the base 2, you have to just divide it by log of 3 to the base 2. Something like this, right? So what my point is, you can do log interconversions. You can do log interconversions very easily by multiplying a constant, because log 3 to the base 2, 4 to the base 3, these are constant terms. So that's why you don't need to put any base of log here. You can just say log n, because it will be some logarithmic identity. Base doesn't matter. The curve is still similar. The rate of growth is still similar. So we can say the time complexity of this function is order of log n. Now you can see we were not able to just directly derive that there are n iterations. No. We saw that it's not I plus plus or I plus equals to 1. It is a multiplication of 2. If it is a multiplication of 2, just think about it. If you are doing I plus 1 or you are doing I into 2, this I into 2 is going to reach n faster, right? If you have to start from 1, one player is, let's say there are two players. One player always moves by one step, whereas the other player moves every time by 2 steps, or multiplication of 2 steps. Can I say this player is going to reach the destination faster? So of course the time complexity is going to be lesser than order of n. Now how much lesser? This is how we analyze. We saw that in every iteration there are just 3 instructions, and if I assume there are k iterations, so there are 3k instructions. What is k? In the first iteration, I is equals to 1. In the second iteration, I is equals to 2. In the third iteration, I is equals to 4. So in the kth iteration, I will be 2 raised per k minus 1. And this is the last iteration which is going to satisfy this condition. That means 2 raised per k minus 1 is going to be less than n. If you take log on both sides, you are going to resolve this, you are going to resolve this, and then you will say k is less than log of n to the base 2 plus 1. That means k never even reaches log n. K is always, k never reaches log n plus 1. K can at max reach log n. Just think about it. If k is less than log n plus 1, can I say k is less than or equal to log n? So we can say the tightest upper bound is going to be some c log n, and in terms of big O, it is going to be order of log n. and we avoid the base because base interconversion can happen in logarithmic terms very easily by just multiplying a constant, and technically constants though we directly avoid. So I hope the overall logic of the problem, that how the time complexity is order of log n, is clear to everyone. So let's start with our next question. So this is the next function in front of us. This is function f9. It takes an input n. You can see it initializes a variable, does a few looping iterations, and then returns the variable answer. So these two are constant terms. These are independent of what will be the value of n. These are just going to be two constant terms. So we'll just keep it like that. Now, the only part of the code which is dependent on the input is this while loop, right? Okay. So let's see. In this while loop, every time what happens? In every iteration, you do the comparison. Then you execute two more instructions. So can I say in every iteration, we execute three instructions. In every iteration, we execute three instructions. So technically, if there are k iterations, if there are k iterations, then total instruction executed is what? 3k is the total instructions. Can I say that? And if every instruction takes c unit of time, then the total time is what? Then total time is 3kc. We just need to figure out what is the value of k as a function of n, because n is the input, right? K is not the input. K, we have assumed that there are total k iterations. We need to figure out how many iterations are there, because once we figure out how many iterations are there, we will be able to figure out how many instructions are there, and we will be able to compute the time also. Now just think about it. Initially the value of n is like normal n. This is the value of n in the first iteration. Then it reduces to n by 2. See, you do n is equals to n by 2. Then it reduces to n by 4. Then it reduces to n by 8, and so on and so forth. Can I say that? So if you just carefully analyze the denominators, can I write it like something like this? N by 2 raised to the power 0, then it reduces to n by 2 raised to the power 1, then it reduces to n by 2 raised to the power 2, then it reduces to n by 2 raised to the power 3, and so on and so forth. If there are total k iterations, then in the, let's say the 0th iteration, let's consider instead of first, let's say this is the 0th iteration, then this is the first iteration, this is the second iteration, and so on, right? You can even consider that, or you can even consider one based iteration, that this was your first iteration, this was your second iteration, this was your third iteration, and so on. If last is your kth iteration, then can I say at last it will be n by 2 raised to the power k? See, n by 2 raised to the power k, because in the 0th, like in the first iteration, it is n by 2 raised per 0. In the second iteration, it is n by 2 raised per 1, and so on. In the third iteration, it is n by 2 raised per 2. In the fourth iteration, it is n by 2 raised per 3. So technically, it should be n by 2 raised per k minus 1 in the kth iteration. Right? See, first iteration 1 minus 1, second iteration 2 minus 1, third iteration 3 minus 1, and so on. So kth iteration is k minus 1. And can I say that when n, till the time n is greater than 0, this loop goes on. So what should be the last value of n approximately for which this loop will go? Can I say the last value should be something like 1, because you are doing by 2 again, right? Again and again you are just reducing by 2. At last this value will become 1. When this value becomes 0, then the loop will end, right? So can I say n by 2 raised to the power k minus 1 is approximately equal to n, equal to 1, right? So you can say n is approximately equal to 2 raised to the power k minus 1. Taking log both sides, log of n to the base 2 is approximately log of 2 raised to the power k minus 1 to the base 2. Log of n to the base 2 is approximately what? K minus 1 log of 2 to the base 2. Log of 2 to the base 2 is 1. So k minus 1 is approximately log of n to the base 2. K is approximately log of n to the base 2 plus 1. Can I say that? So we can say overall approximately we have log n iterations. So if we have log n iterations, so total instruction is was 3 log n, and total time is what? 3 log n to the base 2 into c, which is order of log n, because we will avoid the constant and we will avoid the base. This will become order of log n. So the time complexity of this particular function is order of log n. And how did we calculate? We just saw that in the first iteration the value is n by 2 raised to the power 0. In the second iteration it is n by 2 raised per 1. In the third iteration it is n by 2 raised per 2, so on and so forth. So if there are total k iteration, at last it will be n by 2 raised to the power k minus 1. And because you are doing a division of by 2 by 2 by 2 again, what should be the approximate last value that will be greater than 0? Can I say approximately 1? Because when you do again a by 2, it will become what? 0, right? So we say n by 2 raised per k minus 1 is going to be approximately somewhere around 1. You just take log both sides, simplify it, and k becomes approximately equal to log n. So the time complexity becomes order of log n. So this is kind of like if you do a multiplication of 2 again and again, then you can maybe go for a log n kind of a thing. Not always, but maybe in some cases you can say that maybe you can think about in terms of log n. Similarly, when you are doing a division by 2 again, then not always, but a lot of time it will be somewhere around log n. We are going to see a case when division by 2 is not going to be always log n. We can see that those cases also, but this can be a good way to approach the given question, because here we cannot just directly say that if this was a loop, this loop went for n iterations. No, this loop technically went for log n iterations, because how we are updating the value of n also determines how we are going to converge the corresponding loop. So let's start with this new question. This is the function f10. It takes a value n, and we have to calculate what is going to be the worst case time complexity. So there is only just for loop inside this function, and this for loop is kind of like very interesting. A lot of people, if they will just directly see this for loop, they will feel like the outer for loop is n getting divided by 2 again and again. So technically it might be going log n times, and internally you have less than I. So a lot of people gets a feeling of n log n, but n log n is a wrong answer here. N log n is a wrong answer here. Let me tell you why. Because the value of the inner loop is changing with value of I. It's not constant always, so we cannot just directly rely on n iteration. We have to manually calculate it. If you manually calculate it, then just see, when the value of I is n, the inner loop of j will go from 0 to n. That means n iterations. J will go n iterations. In the once these n iterations are done, you go back and reduce I by 2. So this becomes n by 2. When this becomes n by 2, j goes from 0 to n by 2. So technically j will go n by 2 iterations. When I becomes n by 4, like in the next iteration, I will become n by 4. J will go n by 4 iterations, and so on. At last, I will become n by 2 raised to the power k, because let's say if the outer loop has k iterations, then this will become n by 2 raised to the power k. So j will go n by 2 raised to the power k iterations. So what are the total number of iterations? Total number of iterations is n plus n by 2 plus n by 4 plus n by 8, so on and so forth. N by 2 raised to the power k. I can take n common. This is 1 plus 1 by 2, or you can say 1 plus 1 by 2 raised per 0, 1 by 2 raised per 1, 1 by 2 raised per 2, 1 by 2 raised to the power 3, so on and so forth. 1 by 2 raised to the power k. Right. And this is what? This looks like a GP. And we know that the value of k is going to be what? Log n. The value of k is going to be log n, because we know that this kind of an outer loop works for log n iterations. We have already seen this in the previous question. So we can say that this is equal to 1 by 2 raised per 0 plus 1 by 2 raised per 1 plus 1 by 2 raised per 2, so on and so forth. 1 by 2 raised to the power log of n to the base 2. This is what? Geometric progression. This is geometric progression. What is the sum of a geometric progression? Sum of a geometric progression is a into r raised to the power n minus 1 upon r minus 1 if r is greater than 1, where a is the first term. A is first term, r is the ratio. But if r is less than 1, then this becomes a into 1 minus r raised to the power n upon 1 minus r, where a is the first term, n is total terms, and r is the ratio, right, or the multiplicative factor. So you can see every time the next term is multiplied by 1 by 2, next term is multiplied by 1 by 2, next term is multiplied by 1 by 2. So r is 1 by 2 here. R is 1 by 2 here. The first term is 1 by 2 raised to power 0, that is 1. First term is 1. And how many total terms? From 0 to log n, there are log n plus 1 terms. So n becomes log of n to the base 2 plus 1. So the sum is going to be 1 into 1 minus 1 by 2 whole raised to the power log of n to the base 2 plus 1 upon 1 minus 1 by 2. Let's simplify this. This becomes 1 minus 1 by 2 whole raised to the power log of n to the base 2 plus 1 upon 1 by 2. This will be simplified at 2 into 1 minus 1 by 2 raised to the power log of n to the base 2 plus 1. This will be what? 2 minus 2 by 2 raised to the power log of n to the base 2 plus 1. And what is 2 raised to the power log of n to the base 2 plus 1? Can I say this can be written as 2 minus 2 by 2 raised to the power log of n to the base 2 multiplied by 2. This gets cancelled out. This gets cancelled out. This becomes what? This becomes 2 minus 1 by. What is 2 raised to the power log of n to the base 2? Can I say n? 2 minus 1 by n. And if n is very large, can I say this term is negligible? So this value becomes approximately 2, which is just constant. So can I say the sum of all of these terms is a constant, which is multiplied by n. So the total time is what? Total time taken is n into c, some constant, which is what? Order of n. So the answer of this question is going to be what? Order of n. So let me repeat. What I'm trying to say is, when I is n, j goes n iteration because j is less than n. When I becomes in the next iteration n by 2, j goes n by 2 because j is less than n by 2. And so on. At the last, I becomes n by 2 raised to the power k, so j goes n by 2 raised to the power k iterations. So total iterations are these. We will just sum up all the iteration, we'll get total iterations, right? In every iteration, you can see we are just doing some constant number of operations. So we just need to calculate total iterations. We'll take n common and this becomes a geometric progression. This is the sum of a geometric progression, and the sum of the geometric progression for r less than 1, where the multiplicative factor is less than 1, is this value. If you don't know what is geometric progression, if you have a series like this, 2, 4, 8, so on and so forth. So see, every term is getting multiplied by something, right? And same thing, that is 2. So 2 into 2, 4, 2 into 4, 8, and so on. If let's say you have something like 1 by 3, 1 by 9, 1 by 27, 1 by 81. So this is also geometric progression, but this time we are multiplying by 1 by 3. So geometric progression means you increment yourself with a multiplicative factor. So here the multiplicative factor is 1 by 2. So 1 by 2 into 1 into 1 by 2, then 1 by 2 into 1 by 2, then 1 by 2 raised to the power 2 into 1 by 2, so on up till k. And we know this value k is what? Log n, because this outer loop goes for log n terminologies. So this is going to n by 2 raised to the power log n. If we resolve it with the sum of a GP formula, this becomes the first term. Total number of terms is this. Ratio is 1 by 2. I just put it here. Simplify, and at last we get a term like this. So 1 by n is going to be negligible because we are only dealing with higher values of n. In complexity analysis, we just care about higher values of n. So this overall becomes a constant. So we can say this summation is some constant multiplied by n, hence the time complexity is order of n. So not every time just take a look at the loop and decide that, okay, this is n square, this is n log n or something. If at any point of time you feel that this is not a traditional loop, it has some extra elements, it's a very good way, or it's a very good opportunity to try to debug, calculate exact number of iterations, and then only come up to a conclusion. Now let's start solving this new question, guys. This is a new function. We are going to get an input of n. We just have a nested for loop that depends on the value of n. Let's see. This time, the outer loop is controlled by j. So when the value of j is 1, the inner loop starts from 0. The inner loop starts from 0, goes till less than n, right? So I goes from 0 to n minus 1. And every time you do I is equals to I plus 1. See, j is 1, right? So you do I is equals to I plus 1. So the increment is of 1. Increment is of 1. So how many total iterations? See, from 0 you have to go to n minus 1 with an increment of 1. So from 0 you go to 1, from 1 you go to 2, from 2 you go to 3, so on and so forth up till n minus 1. So total number of iterations are what? Total iterations are n. Can I say that? Just let's take a look at it again. Initially j is equals to 1. If j is equals to 1, this becomes I is equals to 0, I less than n. I is equals to I plus 1. If it is I is equals to I plus 1, this is a normal for loop that is incrementing 1 at a time. You have to go from 0 to n minus 1 by incrementing 1 at a time. So from 0 to n minus 1, you are incrementing 1 by 1 by 1 by 1 again and again. So total iterations are n. So when j is 1, we got n iterations. Okay. What about j is equals to 2? When j becomes 2, I goes from 0 to n. So still I goes from 0 to n minus 1, that is less than n. But this time it becomes I is equals to I plus 2. So every time you are going to give an increment of 2. You are going to give an increment of 2. So just think about it. From 0 you go to 2, from 2 you go to 4, from 4 you go to 6, from 6 you go to 8, from 8 to 10, 10 to 12, so on and so forth up till n minus 1. So can I say these are total n by 2 iterations? Total iterations is what? N by 2, right? Then j becomes 3. I still goes from 0 to n minus 1. But this time increment is what? I is equals to I plus 3. This time the increment is of 3. Just think about it. From 0 you go to 3. From 3 you go to 6. From 6 you go to 9. From 9 to 12. 12 to 15. 15 to 18 and so on. So how many total terms are there? There are total n by 3 terms, right? So total iteration becomes n by 3 only. As simple as that. Right? And so on. At last, j goes to n. I still goes from 0 to n minus 1. And we have an increment of n. We have an increment of n. So can I say total iteration is going to be just 1? Just think about it, right? You start from 0. You check is 0 less than n? Yes. You console.log. And then you do I is equals to I plus n. So I becomes n, right? Is n less than n? No. And the loop ends. So in one iteration, the loop end. So what is the total number of iterations? Total iteration is n plus n by 2 plus n by 3 plus n by 4 plus n by 5, so on and so forth, plus 1. If you take n common, this is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 and so on and so forth, 1 by n, right? If you sum up these terms, this is a like it's a very common series. This sums up to log n. So the complexity of this function is going to be order of n log n. Right. So it looks like this is going somewhere n square, because a lot of time people just see these bounds of n and conclude it is n square, but technically this is order of n log n. Now if you want to check how this sums up to log n, this is technically a harmonic progression. This is technically a harmonic progression. What is the sum of a harmonic progression? Sum of a harmonic progression is actually equals to, like, first of all, let me show you how a harmonic progression looks like. Harmonic progression looks like something like this: 1 by a, first term, then 1 by a plus d. D is the difference. D is the difference, right? Then 1 by a plus 2d. So it's like a reciprocal of ap. 1 by a plus 3d, and so on. At last it is 1 by a plus n minus 1d. And if you take a sum is 1 by d log with the natural base e. You sometimes also call it as ln, ln, right? 2a plus 2n minus 1d by 2a minus d. This is the sum. If you put the values, what is d here? See, what is a here? A is 1. What is d? D is also 1. So 1 by 1 into log base e. 2 into a is what? 2 plus 2n minus 1, because d is just 1, upon 2 minus 1. This becomes log to the base e. 2 plus 2n minus 1 is what? 2n plus 1 by 1, right? And this term is approximately equal to log n, because we can just avoid the basis. This is what? 2n plus 1, right? If n is very large, 2n plus 1 is approximately equal to n. This leads to this sum being log n, and n into log n is n log n. So you can read about harmonic progression, how the formula is derived and everything, but you don't need that, because it's a very general formula. You might have heard about or learned about it in your elementary classes, and you can just put it and get your final answer. So now this is a new function in front of us, function f12. It takes an input n, right? Okay. It has a variable initialized, that's going to be a constant operation, and then it has a single for loop. But this for loop is very interesting. This time we are not doing I plus plus. This time we are not doing I star equal to 2 or I divide equal to 2 or I divide equal to 3. But instead we are doing I into I, right? Okay. So let's see. I starts with 2. Then it goes to what is 2 into 2? 4. Then it goes to what is 4 into 4? 16. Right? And so on. So if you carefully see, this is 2 raised to the power 1. Then it becomes 2 raised to the power 2, because 2 raised to the power 1 into 2 raised to the power 1 is 2 raised to the power 2. Then 2 raised to the power 2 into 2 raised to the power 2 become 2 raised to the power 4. Next term should be what? 2 raised to the power 8, and so on. The final term of this series, let's say if it is some 2 raised to the power k, that is the final value of I, which should be less than or equal to n. Can I say this will be some final value of I which will be less than or equal to n? So we can say 2 raised to the power k is less than or equal to n, taking log both sides. This will become k is less than or equal to log of n to the base 2. So we know that the last term is going to be something like this. But just calculating this much, does it give us the complexity analysis? No. Because it's not like these are the number of iterations. No. K doesn't denote number of iteration here. This is something very important. K doesn't denote number of iteration. Can I say that? K doesn't denote number of iteration. If you just carefully see, in the first iteration, you are at 2 raised to the power 1. In the second iteration, you are at 2 raised to the power 2. In the third iteration, you are at 2 raised to the power 4. In the fourth iteration, you are at 2 raised to the power 8. And so on. Let's say in some tth iteration, you are at 2 raised to the power k. Can I say that? Can I say that? So technically, if you check the powers, then in the first iteration, the power is 1. In the second iteration, the power is 2. In the third iteration, the power is 2 raised to the power 2. In the fourth iteration, the power is 2 raised to the power 3. Can I say that? See, in the fourth iteration, power is 2 raised to the power 3. So on and so forth. Can I say in the tth iteration, the power is going to be what? 2 raised to the power t. Some 2 raised to the power t. Right? See, again, in the first iteration, if you just look at the power is 1. In the second iteration, power is 2. In the third iteration, power is 2 raised to the power 2. See? So, you can write it as 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. So, in the tth iteration, technically it should be 2 raised to the power t minus 1. 2 raised to the power t minus 1. See? For 1 it is 0, for 2 it is 1, for 3 it is 2. So, for the tth iteration, it will be 2 raised to the power t minus 1. And can I say my final power is what? K. So, I can say 2 raised to the power t minus 1 is equals to k. Taking log both sides. T minus 1 log 2 to the base 2 is equals to log k to the base 2. T is equals to log of k to the base 2 plus 1. And what is the value of k? K, the max value of k can be log n. So t becomes log of log n plus 1. And this is what a lower degree term. So the overall complexity becomes order of log n. This is a very different type of a question. Let me show you guys again. Just think about it. Let's just take a look at the value of I. I goes from 2 raised to the power 1 to 2 raised to the power 2 to 2 raised to the power 4 to 2 raised to the power 8, so on and so forth, 2 raised to the power k. Right? This is the final value of I. This is the final value of I, which will be less than or equal to n. If you take log both sides, k will become less than or equal to log n. But this is not the number of iterations. K is not the number of iterations. You can see, right? Because k denotes the final power of I. But what is the number of iteration? Number of iteration is, let's say 1, 2, 3, so on and so forth, some t. Let's say t is the final number of iteration. Total iterations is t. T denotes total iterations. How can you calculate the value of t? You can calculate the value of t based on the powers. Because powers are in a GP again. See, in the first iteration, power is 2 raised to the power 0. In the second iteration, power is 2 raised to the power 1. In the third iteration, power is 2 raised to the power 2. In the fourth iteration, power is 2 raised to the power 3. So in some tth iteration, power will be 2 raised to the power t minus 1. And we know the final power we considered was k. This was the final power of I. So 2 raised to the power t minus 1 will be equal to k. Taking log both sides, simplifying will give us the complexity as order of log n, because complexity depends on number of instructions. Number of instructions here depend on number of iterations, because in every iteration we just have 3 instructions. So 3 into number of iterations is going to be the total number of instructions, and 3 is a constant. So our complexity will be order of number of iterations. Number of iterations are log of log n. This is a very interesting question. I would highly recommend you guys to try to analyze this question again yourself. I have just very smoothly and simply solved it, but I would recommend you to go again and try to analyze it and see what can be done here. But I hope the overall solution of the problem is clear to everyone.